This will be the first of two lessons on graphing experimental data. In this lesson, we're going to make the graph. In the second lesson, we'll determine the slope of the graph. The data we have here, L in meters, t squared in seconds squared, is something that you might get for a pendulum. The reason I have t squared, that represents the period of the pendulum squared, is because there's a linear relationship between the square of the pendulum period and the length of the pendulum. So we'll be able to see a line on our graph instead of a parabola or some other sort of curve. The directions here would be to first make a graph of t squared versus L using the data in the table to the left. An immediate question that arises is what goes on the vertical axis and what goes on the horizontal axis. Whenever you have A versus B, the thing that comes before the word versus always goes on the vertical axis, and the thing that comes after the word versus goes on the horizontal axis. That's also the case if you happen to have A as a function of B. The word before as a function of would go on the vertical, and the word after would go on the horizontal axis. So that's the way these things work. Well, we have t squared versus L. Before the versus we have t squared. After the versus we have L. So t squared will go on the vertical axis. L will go on the horizontal. Continuing on in that first instruction, says before drawing your line, also graph the point that is the average of the values of t squared and L. There's a rather complicated statistical method for determining a best fit straight line. It's called least squares fit of a straight line. It's more complicated than we need to do here, but if you ever happen to do that, it turns out the best fit straight line goes through the average point of the data. And so we would want to calculate the average of the L values and the average of the t squared values and just force our line to do that. We're making it by hand, so we can do that easily. The average value of L squared happens to be 0.61 meters. The average value of t squared here happens to be 2.32 seconds squared. So those are things we're going to need. We'll want to mark that point in some distinguishing way, and a circled X works well. There are components that every graph should have, and for experimental data, the first thing it should have is a descriptive title, something that tells the reader at a glance what the graph represents. Another thing it should have is axes labeled with the quantity they represent and the correct units for that quantity. And then select a scale for each axis that makes the graph as large as possible, using more than half of each axis, while still being easy to plot points. Let's start off with a good title for our graph. If I title my graph Period Squared versus Pendulum Length, that's pretty descriptive. Somebody can tell at a glance what that thing represents. Next thing I want to do is put labels on my axes that represent whatever that axis represents. My vertical axis I'm going to have be t squared. It'll have units of seconds squared. And so I've got both the quantity represented on the axis, t squared, and the appropriate units for it. My horizontal axis will be L, and it'll have units of meters. So I've got both of those things. Now I have to select a scale for each of those axes. Before I do that, I'm going to talk a little bit about picking scales. Let's suppose you're making a graph and you decide that each major division on the graph, and most graphs have 4 fine lines between each major division, so they actually split it into 5 parts. Let's suppose you decide to make each major division represent 1. It could be 0.1 or 0.01, but some power of 10 anyway, or some multiple of 1. If that represents 1, then each fine division on there would represent 0.2. I can do that in my head pretty easily. I know that this is 0.2, two of them is 0.4, 0.6, 0.8, and so forth. So that might work. But it may be that selecting that as your major division size shrinks all your data into a fraction of the graph. We want to use as much of the graph as we possibly can. More than half of it is best. Well, then you could double it. And so maybe you let 2 divisions equal 1 on here. That's also a good way to go, because then half or one of those divisions would equal 0.5, and each fine division on here would be 0.1. So 0.1, 0.2, 0.3. That's easy to figure out as well. Now, suppose I decided to let 3 divisions equal 0.1. That would not work so well. And here's why. Each major division on here would be 0.33, and then I'd have to divide 0.33 in my head to know what each fine division meant as I'm graphing those. So don't let 3 divisions equal 1. However, I could go to 4. If I go to having 4 major divisions equaling 1, then each fine division is equal to 0.25, or each major division by itself is 0.25, and each fine division is 0.05, 1/5 of that. I can do that in my head. 0.05, 0.10, 0.15, 0.20, 0.25, and I could keep track of that okay. One other possibility, I could have 5 major divisions equal 1. If I do that, each major division would equal 0.2, or 0.20. So this would represent 0.20, and 1/5 of that would be 0.04. So each fine line on here would be 0.04. And I can keep track of that in my head. No fractions or decimal places after the 4. I could think of it 0.04, 0.08, 0.12, 0.16, and 0.2. So those all work well. Either a 1 represents a major division, 2 major divisions equals 1, 4 major divisions equals 1, or 5 major divisions equals 1. Any of those things work for multiplying my scale to get all of my data as spread out as possible. Now let's consider the data that we have again. The graph paper I'm using, by the way, has 15 divisions on the vertical axis. That's the one that'll represent t squared. And it has 20 divisions on the horizontal axis. That's the one that will represent L here. Well, if I consider the L first, this is pretty much all the way up to 1. If I have each major division equal 1/10 on there, I'll only use 10 of the horizontal divisions, and I've got 20. So on my horizontal scale, I can actually double things up. And that's the way that I'll want to do it. So each 2 divisions will equal 0.1 on my horizontal scale. And what that means is this will be 1.0 over here. Halfway down there, 10 divisions will equal 0.50, and every 2 divisions on here will equal 0.10. So there's my horizontal scale. By the way, 0 is down here on this one. Now let's consider the vertical scale. When I look at the range of values for t squared, it goes from 0.85 up to 3.84. That's actually a little bit less than 3 for the span of my data. So I want my vertical axis to somehow reflect that. When I look here, if I actually have each square represent 1, I'd only be using this much of my vertical axis. I can double that, have each major division on here represent 2. I'm still using less than that. I can double it again. If I let 4 major divisions on here equal 1, then this would be 1, here's another 1, and here's another 1. I'll finally use more than half of my axis. When I consider my data again, the biggest value on here is 3.84. I think I'll let the very top of my axis represent 4. So I'll let that top point up there be 4.0. Every 4 of these is going to be 1 second squared. Now when I look at this last thing down here, I've only got 3. It'll take 4 of these to represent 1, so each one of these is 0.25. This would be 0.75, 0.50. The bottom of this axis is 0.25. It's not 0. That's okay. When you're graphing experimental data, if you don't have any data below a certain point, you don't need to worry about it. Also, we're after the slope. I don't care what the intercept is, the vertical intercept. All I'm after is the slope, and so I don't need to have the origin on my axis to figure that out. So I've got my scales figured out. Now I'm going to plot the data points. Turns out I've already done that. Here's what my finished graph looks like. I have a title, labeled axes with the units they've got on both scales, and I've got my labeled axes. I've got the scale identified on here. And I've got all the data points. The average data point is distinguished by a circled X. That's what it happens to be. The next thing we'll do is determine the slope of this graph. That will be in part 2.